The Prandtl-Meyer expansion waves. The present section treats gradual change in the flow angle and that are primarily expansive. They widen the flow area and increase the Mach number and velocity as stated here. Mach number and velocity, the property change accumulate in infinitesimal increment and the linearized relations are used. The local flow deflection are infinitesimal so that the flow is nearly isentropic. This figure shows 4 examples of the Prandtl-Meyer expansion waves, one of which shows in the C part. Phase the test for gradual change. The gradual compressions of A part is essentially isentropic, this type, with a smooth increase in pressure along the surface, but the Mach angle increase along the surface and the waves tend to coalesce farther out into an oblique shock wave. The gradual expansion in the B case cause a smooth isentropic increase of Mach number and velocity along the surface here with diverging Mach phase form. The sudden compression of part C cannot be accomplished by Mach phase and oblique shock forms this shock wave, and the flow is non-isentropic. This could be what you would see if you looked at the A part from far away. Finally, the sudden expansion of the D shape is isentropic and forms a fan of centered Mach waves emanating from the center, this point. Corner. Note that the flow on any streamline passing through the fan changes smoothly to higher Mach number and velocity in the limit. As we near to corner, the flow expands almost discontinuously at the surface. The cases in this picture, case A, B, and D, can all be handled by Prandtl-Meyer supersonic wave theory of this section. So in this section we have as we said in the part C, we have shock wave and no Prandtl-Meyer expansion wave, and A, B, and D are the cases that can be handled by the Prandtl-Meyer supersonic wave theory, first formulated by Ludwig Prandtl and his student Theodor Meyer in the 20th century. Earlier 20th century. Note that none of these discussions make sense if the upstream Mach number is subsonic. So we should write a note. None of these. Example. Makes sense. If the upstream Mach number is subsonic, since Mach wave and shock wave patterns cannot exist in subsonic flow. Mach wave and shock wave patterns cannot exist in subsonic flow. The Prandtl-Meyer perfect gas function. The next subsection in this chapter is the Prandtl-Meyer perfect gas function. Consider small, nearly infinitesimal flow deflection d theta such as occurs between the first two Mach waves in the picture here, A and B. Small, nearly infinitesimal flow deflection d theta as shown in the picture here. D theta, so we can write a relation between the at first we have beta, the first angle between the first two exist wave, and also we can write a relation for the part A d theta. Since the flow is nearly asentropic, we have the frictionless differential momentum equation for a perfect gas. Frictionless differential momentum equation for a perfect gas. dP Combining these equations to eliminate the dp, we obtain a relation between turning angle and velocity change, which is d theta This can be integrated into a functional relation for final turning angle if we can relate v to Mach. We do this from the definition of Mach number. For the Mach number we have v on a multiplied to Mach number. Substituting to the above equation, we can obtain this relation for a Prandtl-Meyer wave. Finally, we can eliminate the dA on A because the flow is isentropic and hence A0 is constant for the page gas. We have this relation for A stagnation point. Sound at finally to dA on A can be obtained as this relation. Eliminating dV on V from the previous relation, we obtain relations solely between turning angle and the Mach number. D theta equals to -1 Before integrating this expression, we note that the primary application is to expansion, increasing Mach and decreasing theta. Because this part is positive, negative, and there is a opposite sign in the changing of d theta, we increase. If the theta increase, we have d and a decrease. Therefore, for the convenience, we define the Prandtl-Meyer angle Prandtl angle which increase when theta decrease and is 0 at the sonic point. Increase when theta decrease and is 0 at the sonic point. Or we can write the Prandtl-Meyer angle at Mach number or sonic condition. Thus, we can integrate the d theta relation as stated here to obtain the d theta equals to this relation dma on the Mach number. With integration of this relation, we can think we had this relation also. dw consequence of the Prandtl tangent inverse minus tangent where k on k plus 1. This is the Prandtl-Meyer supersonic expansion function. Which is plotted, also can be plotted in the diagram. The angle omega change rapidly at first, and the levels of at high Mach number to a limiting values when the Mach number tend to, let me write again the relation here. Where k equals 2 plus 1, the angle omega change rapidly at first, and the levels of the at high Mach number to a limiting value, the maximum angle of the for A. Thus, a supersonic flow can expand only through a finite turning angle before it reaches infinite Mach number, maximum velocity, and zero temperature. Gradual expansion or compression between finite Mach number and from, for example, 2, neither of which is unity, is computed by relating the turning angle delta W to the difference in Prandtl angle for the two conditions. We have at Mach 2 minus the change delta omega may be either positive or negative. Positive for expansion, and negative for compression. There are applications for the application to supersonic airfoils as these pictures. The oblique shock and Prandtl-Meyer expansion theories can be used to patch together a number of interesting and practical supersonic flow fields. This marriage, called shock expansion theory, is limited by two conditions. Except in rain instances, the flow must be supersonic throughout, and the second is the wave pattern must not suffer interference from wave formed in other parts of the flow field. In other parts of the flow field. A very successful application of shock expansion theory is to supersonic airfoils, as shown here. Shows two examples, a flat plate and a diamond-shaped foil. In contrast to subsonic flow design, this airfoil must be sharp leading edge which form attached oblique shocks or expansion fans. Rounded supersonic leading edge would cause detached bow shock, greatly increasing the drag and lowering the lift. In applying shock expansion theory, one examines each surface turning angle to see whether it is an expansion or a compression to the surface flow. The figure A shows a flat plate foil at an angle of attack. This shape, flat plate. There is a leading edge shock on the lower edge with the flow deflection theta equals to alpha as shown, while the upper edge has a shock on the lower edge with the flow deflection, while the upper edge has an expansion fan with increasing Prandtl-Meyer angle equals to the angle of attack. We can compute P with expansion theory and P second with the oblique shock theory. The force on the plate is thus calculated as CB, where C is the chord length and B the span width. This force is normal to the plate and thus the lift force normal to the stream is F and the drag Prandtl to the stream is the perpendicular to the lift. The dimensionless coefficient CL and CD have the same definition in low speed flow, except that the perfect gas law, we can write the relation for the dimensionless drag force T1 second of BC. The typical supersonic leap coefficient is much smaller than the subsonic value, but the lift can be very large because of the large value of the supersonic lift. Coefficient is much smaller than the subsonic value. CL but the lift can be very large because of the lift large value of at the supersonic speed. The diamond foil in the picture, as shown here, adds two more wave patterns to the flow. At this particular alpha less than the diamond half angle, there are leading edge shocks on the boot surface, the upper shock being much weaker. Then there are expansion fans on each shoulder of the diamond. We can write the expression for the airfoil Thin-Airfoil Theory. Where we have these relations. CL tangent alpha CL alpha 4 alpha square minus 1 and the drag also can be written as this relation. Y prime A square plus Y prime L square, where the Y prime can be calculated as the integration of the dy on the x where C is the length of the wave. This is the end of the chapter 9. The next chapter is the open channel flow, separately discussed in the various videos.